IGCSE Computer Science, Syllabus Statement 1.3.1a, understand and define the functions of not, and, or, NAND, NOR, and XOR gates. So, this is the start of topic 1.3, which is the longest topic in the course, because it covers hardware and software. And yeah, it's just pretty long. So we start off with logic gates. So what are logic gates? Well, these are logic gates here. Well, 6 of them. And they're basically related to binary. So logic gates are used in electronic circuits in computers. So your computer in front of you, or like phone or iPad or whatever you have, it's made up of thousands of these logic gates. And we're about to find out what they are now. So they basically take in binary input and well, output binary as well. So input binary, output binary, and you'll see how this works. So we'll start with the NOT gate. So the NOT gate looks something like this. You're going to have to know these symbols for the exams if you're constructing logic circuits. However, on the 2015 winter papers, I noticed that there were no logic questions, which was a bit sad, because this is quite an easy topic once you get the hang of it. But yeah, just in case your exam actually does happen to have logic in it, then you might as well be prepared. So yeah, when we see a logic gate, we have an input and an output, so A and X respectively. And what we can do is we can give A a binary number, and X will give a binary number, or it'll output a binary number. So, say for example, we gave this 0, then 1 would come out in the NOT gate. And we can actually, and vice versa, but we can actually represent this using something called a truth table. So input 0, output is 1, input's 1, output is 0. So a NOT gate is basically the opposite. So basically what this is here, this small thin line, is basically a wire. So in a physical circuit, like NOT gates, and remember that binary we can say is kind of like electricity, so off and on is 0 and 1. So it's kind of that idea. So when you pass electricity into a NOT gate, then no electricity comes out. And that's sort of what the NOT gate represents. There's also logic notation for this gate, for every gate actually, but this is the one for this gate, so it's not A. And then there's Boolean algebra, which is this. So you're going to have to know this for the exam as well, both of these. And we'll get back to using these when we look at logic circuits, as these will become a little more complex. And this course doesn't ask you to simplify it, but it's still good if you can, like, you know. But I mean, I don't know. They might ask you to give the full Boolean algebra expression, but you know, it's still cool if you simplify. So let's look at the AND gate. So the AND gate looks like this, and you'll notice that it takes 2 inputs instead of 1, like the NOT gate. Well, this behaves a bit differently. So we get inputs A and B and output X. So the truth table would look something like this. So if we give A0 and B0, the output would be 0. A0 and B1, the output would be 0. A1 and B0, the output would be 0. But A1 and B1, the output is 1. So you can kind of see why it's called the AND gate. So this and this have to be 1 in order for this to be 1. So the logic notation would be X equals A and B. Boolean algebra would be X equals A dot B. And you'll also see when we look at logic circuits that we can use, as said, logic circuits, basically a bunch of logic gates, and you'll see how that works. And I'll also show you that, like, logic circuits can be used to perform functions such as adders and subtractors can be built with logic gates, and I'll show you a bit of that later on in another video. So we had 2 inputs for the AND gate, but we can actually have more. We can actually have 3, 4, 5, or however many we like. So this is how the truth table would look if we did this. So we'd have the inputs A, B, and C, and the output X. So A and B and C give 0. Rather, 0 and 0 and 0 would give 0. 0, 0, 1 would give 0, and so on, actually, until we get to this, where it's 1. So you can see that all of these have to be 1 in order for this to be 1, because it's A and B and C. The OR gate is similar idea, but of course a different truth table. So again, we get the inputs and the output, but for OR, 0 or 0 makes 0, 0 or 1 makes 1, 1 or 0 makes 0, and 1 or 1 makes 1. So why is this the case? Why is 1 or 1, why does 1 or 1 make 1? Well, basically, the OR gate isn't exclusive, and which is what the XOR gate is for. It's exclusive OR. So the OR gate isn't exclusive. It can include multiple 1s for its input in order for the output to be 1. But as long as, basically for the OR gate, as long as any input has 1, or any, like, 1 or more inputs have 1, then the output is 1. So the logic notation would be this. Boolean algebra would be x equals a plus b. So 3-input OR would look something like this. So remember that like any input, 1 or more inputs can be 1 in order for x to be 1. So it looks like that. So the XOR gate, as you may have guessed, would look something like this. This is the, of course, the gate itself, and the truth table looks like this. So as you notice, the XOR gate will not produce 1 if both these inputs are 1. So it'll only accept one or the other, basically. So it's exclusive. And the logic notation for this would be this. Would be A XOR B. Boolean algebra would be A plus circled B. Now, I don't know if this will be acceptable if you write this in the exam, but you know, try it out, because this is actually the official symbol for XOR. So yeah. So what would a 3-input XOR truth table look like? Well, you might find it a bit weird at first, but it actually does kind of make sense. So let's take a look. That looks fine, that looks fine, that looks fine. Okay. So here we get 0, 1, 1, 0, which can be expected. If you cover up the A, B XOR C would make 0, but there's a 0 here, so doesn't that... Well, no, not really. Because the XOR gate actually kind of works like this. So only one input, and only one input, can be 1 in order for the output to be 1. So if it's 0 or 2 or more, then the output is 0. So that's how a multi-input XOR, well, an XOR gate itself works. So now we have a few more gates left. We have NAND and NOR. So what are they? Well, we got the N from NOT and the AND from AND. So that would make NAND, wouldn't it? So NOT AND NAND. Well, that's it. So it's basically you put a NOT gate in front of an AND gate. Well, when I say in front of, I mean like the output of the AND gate will be the input of the NOT gate, and you can make a NAND gate. Now, NAND gates are quite special, and we're going to see how they are special later, but they are special, and we'll get to that. So let's take a look at the truth table for a NAND gate. I was about to say trace table, which is what we'll cover in practical problem solving and program. I don't know why that title is so long. Why can't it just be problem solving? Like, it's not really programming. It's like, I mean, it kind of is programming, but like pseudo programming. It's alright. So here we have a 1, here we have a 1, here we have a 1, and here we have a 0. Now what do you notice about the outputs here from this truth table? Well, if you go back back to where we looked at the AND gate in this video, you'll notice that the outputs are the exact opposite. So the AND gate's truth table would be 0, 0, 0, 1, but the NAND gate's truth table would be 1, 1, 1, 0. And the logic notation was obviously this. Boolean algebra would be this. So this, just the A dot B would be an AND, so we just stick a dash on the top of it to make it NAND. So it's not AND. It works like that. So a 3-input NAND would look something like this. So go back to the 3-input AND, and it's basically the exact opposite. So the NOR gate is the same principle. We stick a NOR gate in front of the OR gate. Oh, sorry, stick a NOT gate in front of the OR gate to make a NOR gate. So NOT OR. So let's take a look at the truth table for this. So 0, 0, 1 as expected, 0, 1, 0, 1, 0, 0, 1, 1, 0. So this was expected because it's the opposite of the OR gate truth table. And same thing with the like bar up here. It's knotted. So the entire statement here is knotted. So a 3-input NOR would look something like this. Ooh. So now this isn't actually listed in the syllabus, but it's still good to know it because, like, why not? I mean, why are they getting us to do XOR without having to put a NOT in front of it? So we get XNOR, not NEXOR, XNOR. So like exclusive NOR. So that's basically what it looks like. It's not, again, it's not in the syllabus, so I wouldn't bother trying to impress the examiner by using this. But if you want to, go ahead and try it. It's like, yeah, well, yeah, whatever. Alright, so the truth table for this would, of course, be the NOT of the XOR. So it would be 1, 0, 0, 1, and of course the logic notation would be that, Boolean algebra would be that. So let's take a look at a 3-input XNOR gate before we wrap up this video. Just so you get the idea, it's the opposite of the 3-input XOR gate. This is IGCSE Computer Science Syllabus Statement 1.3.1b. Use logic gates to create electronic circuits. So as you can see, this looks a bit different. So what I'm using is a logic simulator called Logisim to create electronic circuits with logic gates. So what you're going to need to do first is, if you haven't already, watch 1.3.1a to understand all of these logic gates here, because you're going to need to know the logic gates and their truth tables in order to actually understand what's going on here. So once you've done that, we can get started. So here we have input, so we can have 2 inputs, and here we have output, so we can have an output here. So just to refresh your memory, I'm just going to click this and put this here, drag the wire here. This is pretty much how a logic gate, well, the NOT gate in this case, will work. So it's basically, as you can see, inverses the bit. So we give it 1, output 0, give it 0, and output's 1. I won't go through all of the gates now because that's all covered in that video, 1.3.1a. So go ahead and watch that to actually understand, but I was going to show you an example of how this works. So you just click this for to change between 0 and 1. So let's try creating a circuit. So Well, we learned about logic gates in the last video in order to create circuits. And in the exam, you're going to need to create circuits as well as look at them and then produce truth tables for the circuits, which we'll go through in the next video. So, last time I recorded this video in my older series, this video was about an hour long, but this video, this one right here, should be 10, maximum 15 minutes. Hopefully not that much, but we'll see. Should probably stop talking and get on with this. So, we're going to be using the NOT, AND, OR, NAND, NOR, XOR, and XNOR gates. So, let's create a basic logic circuit. We can use the AND gate, the NOT gate, and let's do the NOR gate, and yeah, let's pick the XOR gate. Now this circuit is quite special because, well, actually you're going to see why just in a second, but once I've connected these wires, that is. But basically, you're gonna find out why this is special, and you're gonna see that. Well, yeah, that's it. I don't want to spoil anything too much, but you'll see what I mean. So I've dragged these wires here and to the output. So 0. Well, actually, let's label these to make it clear. This is A. This is B. This can be X. So let's try changing the inputs. So 0, 0 makes 1. 0, 1 makes 0. 1, 0 makes 0. And 1, 1 makes 0. So what do you notice about this? Well, in case you haven't noticed, take a look at the output when we give it different inputs. 0, 0 makes 1. 0, 1 makes 0. 1, 0 makes 0. And 1, 1 makes 0. If you haven't noticed, this is actually the truth table for, well, it has the same, well, this circuit has the same truth table as another logic gate. So let's find out which one. So we'll do the same thing here. I think I can copy this. Yep. Let's move this over here. I'm just going to move the B up a bit. So this is why I told you to look at the other videos so you can actually understand the truth tables for the other logic gates. So you'll notice 0, 0 makes 1, 0, 0 makes 1. 0, 1, 0, 1 makes 0. 1, 0, 1, 0, both make 0. And 1, 1, 1, 1 makes 0. So this entire logic circuit can be simplified to this little logic gate here. So that's one of the things that you may be tested on in the exam. So they might ask you to give the logic gate, which can, well, yeah, give the logic gate which this can be, the circuit can be simplified to. So like, yeah, it's the reason actually is because if you're buying physical logic gates, like if you're building a computer, then it's good to keep it simple so you can save money. That, and I'm just gonna move the. Actually, it doesn't really matter. It's kind of weird. All right. So let's get rid of that and try something else to wrap this video up, because, well, this video is kind of, well, I think it's going to be long if we don't. So this logic circuit will have 3 inputs. So we can name these A, B, and C. So we're going to try to create a circuit using all of the logic gates that we've learned so far, all 7 of them. So we start with the AND, put that there. The NOT, definitely, let's put that there. The OR, I might have to spread it out a bit actually, because circuit might be a bit big. Let's move that down. Oh, missed that. There, okay. So, A, B. Will this work? Yeah, I think that'll work. And we can have C there, of course. So let's try adding the OR gate. Put that there. And we can drag A here. This might look a bit weird. We can have the XOR gate here. I know this seems really boring. Sorry for that, but what you can try to do is get used to doing this on paper, actually, because that's what you're going to have to write the exam in. That's what you're going to have to draw logic circuits in as well. So we have the NOR gate here, and we just need to add the NAND gate. And finally, we can add our, we have 6 now. We can add our final XNOR gate right here. So we drag this input down here, or this wire rather. And then we can have an output here. So if you try to, if you're using the simulator, and you try to click the, I'm just going to put that there. If you try to click the inputs, you get something like this. You can try out these different combinations, see what outputs you can get. Now I won't go much on the truth tables this video, because as said, we're going to look at that in another video, which is actually the next video. So what we're actually going to do is we're going to take both of the logic circuits that we learned in this video, and then produce truth tables for those circuits. So if you've done this on paper, you might want to save it. If you've done it in the logic simulator, you might want to save it for the next video. IGCSE Computer Science Syllabus Statement 1.3.1c, produce truth tables for given logic circuits. So in the last video we looked at 2 logic circuits, building them in a logic simulator, but we didn't look at the truth tables for those circuits. So this is what we're going to be doing today. So yeah, that's pretty much it. So if you don't remember what a truth table was, watch the first logic video, because that video has the truth tables for all of the logic gates. A truth table is basically a table which shows you the output of a gate or circuit with all possible inputs, and you'll see what I mean in a second. So let's take a look at this logic circuit. This is the first one that we made in the last video, if you recall. So we have 2 inputs, A and B, and an output X. Now what we can do to make our lives easier is to add intermediate or middle values. So like L, M, and N. So these will be the outputs in these 3 gates here. The outputs of these 3 gates here, just to make life a little bit easier for us when we do our truth table. So basically L is not A, M is A and L, and N is A nor B. So it's pretty much like that. And then of course X is M, X, or N. So we'll look at that in a truth table right now. So we have A and B as inputs. We have 0, 0, 0, 1, 1, 0, 1, 1. So all the possible inputs of the circuit. Then we have L, M, N, and X. So these are the intermediate values, and this is the output. So not A is simply not A. So not 0 is 1. M is A and L. A and 1, well, 0 and 1 makes 0. N is A nor B, so that would be 1, because it's like, it can only, well basically, yeah, it can only be 0. Yeah, it's actually, it can only be 1 if both of these are 0. So if any of these were to be 1, or even both of them were to be 1, then this would be 0. That's what I meant to say. And of course, the output, which is m XOR n, we just take a look at these, and it looks like the output will be 1. So then we have 0 and 1. So not A, it's of course again 1. A and L, so that would be 0 and 1, so that would be 0. A nor B, so this would be 0, because as said, it can only be 1 if both of these are 0. And m XOR n has to be 0. And we could do the same thing. This would be 0, 0, 0, 0, 0, 0, 0, 0. So we get the output of this circuit 1, 0, 0, 0. And as said in the last video, this is the truth table for a NOR gate. So we could have, again, simplified this entire circuit into this gate right here. So there's no need to buy this part, or this part. You need to buy this part. So in the exam, you're going to have to, like, well, you're probably going to have to, I'm going to say probably because I don't know what, I don't know what's going to be on the exam, but you're probably going to have to simplify a logic circuit into a logic gate. And this is pretty much how to do it. You look at the output of the truth table for the circuit that you've made and think to yourself, well, what if this is similar to any of the gates that I know? That's pretty much what you do. So now we get to this bigger logic circuit, and this is the one, if you remember, that we made with all of the 7 gates that we learned about. So we have our inputs, our intermediate values, and our output. So what I've decided to do is, well, I mean, actually, forget what I was going to say. What you could try to do is try to, wait here, let me just set this up first. So we have all our possible values for the inputs, and of course we have our other values. So what you could do on your own, if you want to, is you could try to figure this out for yourself just to get some practice. If you don't want to, just continue watching and we'll go through it. Okay, so let's look at L first. That's A and B. So 0 and 0 must make 0. A or B, 0 or 0 must make 0. This must make 1. L nor M must make 1. Because if you remember, in the OR gate, the output is 0, 1, 1, 1. So in the NOR gate, the output must be 1, 0, 0, 0. So, which means that if both inputs are 0, then the output is 1. L NAND O must be 1, because in an AND gate, this would be 0. M XOR N, this must be 1, because there's only one 1 in the input. P XNOR Q must be 1, because an XOR gate would output 0. So you get the idea, pretty much. So it's the same for this row, and so on. And it's good to get practice doing this on your own, because in the exam, of course, you might have to do this. So that's pretty much it. Sorry that I didn't go through every row. I thought that it would be quite tedious, because you sort of get the idea of how this works already. So thanks for watching, and I'll see you guys when we look at the next statement. IGCSE Computer Science. This is syllabus statement 1.3.1d. Produce a logic circuit to solve a given problem or to implement a given written logic statement. So this video is, as the syllabus statement says, we're going to be creating logic circuits using, logic statements or a given problem. So we'll start with the logic statement because it's easier. I mean, I wouldn't say it's easier. They're about the same, but it's simpler just so you can get the idea. So let's go ahead and get started. So here we have a condition. X is 1 if A is 1 and B is 1, or A is 1 and C is 0. Here we have the logic statement, X equals A and B, or A and not C. Then we have the Boolean algebra, X equals A and B, or A and not C. So we're going to create a logic circuit using this. Yay! So what you're going to do first is you're going to do the brackets first. I'm just going to put my computer on charge. Okay, so yeah, do the brackets first. So we start with A and B. So we have A here, B here. Let's add an AND. So we have A and B. So there we are, that was easy. Next bracket, A and not C. Okay, so I'm just going to move this up here. So it's a little bit, in fact, I'm going to get rid of this and draw this again. Alright, so it's A and not C. So let's start with the not C first. So we need a NOT gate. Attach that onto C. Then we have A and not C. So we need an AND gate. And this will connect, of course, C, or rather, not C, and A. Now note the use of this circle here, and that basically means that this wire is connected with this, and this has no circle because the wires are just crossing, they're not connected. So make sure that you do this in the exam when they ask you to, if they ask you to draw a logic circuit, because that'll come like in handy if you're like building big circuits and crossing wires and such. So yeah, so now that we're done with our two brackets, we can move on to the rest. So that's the OR right here. So we just add it here, and we drag it here and here. And then we can extend that to the output. So we can give this a try. So it should work. A and B should work. So that works, A and B. A and not C, that works, because A and C wouldn't work. And we can also try some other things like B, C and B, some other stuff. If all of them were on, then that would be on. If it was just A and B, that would be on. Well, actually, yeah, it's A and B, right? Yeah, it's supposed to work. Yeah, if all of them were on, then that would also work. Okay, so that's pretty much it. We've built our logic circuit. So what next? Well, we create the truth table. Now, to save you some trouble, we actually could create intermediate, like assign intermediate values here, here, and here, and then trace like the wires and see where like what outputs and what inputs into where. And well, we don't have to worry about that because I'm going to teach you how to fill in a truth table with just the logic statement. So let's go ahead and go to another app, Numbers, and we can do that. So I'm just gonna, I keep forgetting the, okay, so X equals A and B, or A and not C. So let me just write that up somewhere here. Just put it here. X equals, was it A and B, or A and not C. So that's our, what's put up here, that's our statement, and we're going to create the truth table with this. So we need the inputs A, B, and C. We need the output X. So here's how you do it. First, you can fill these in with the numbers 1, 1, 1. We need another one. 0, 0, 1, 1, 0, 1, 1. I could probably do this. No, that doesn't work. Let's try that. No, that's not the. This is annoying. Let's try this. Okay, Alright, never mind. We'll just continue this. Okay. And then we 0, 0, 1, 1. This better work. Yay. Okay. So, created our all possible inputs. So now, again, we look at the brackets, A and B. Let's find where A and B are 1. So, that's 1. And that's another one. And let's find A and not C. There's 1. And the rest should be 0. Or is it? Yeah, I think that's pretty much it. And we can test it. So if we remember 4, 0, well, we can remember 0, 0, 0, 0, 1, 0, 1, 1, 0, 0, 0, 0, 1, 0, 1, 1, and that works. Check that out. It actually works. So, again, just a tip, if you don't want to waste your time tracing the wires and the logic circuits, you can just do that if you're given a logic statement. So what we're going to look at now is another sort of, we're not the statement, but we're going to look at a problem. So I've got one here. A gas fire has a safety circuit made up of logic gates. It generates an alarm, X equals 1, in response to certain conditions. And here are the conditions. And yeah, so, didn't mean to do that. This question I took from the 2015 exam from May, June. And I think it's a pretty good question as an example because it's exam style and you can get used to how the questions are worded. So let's go ahead and do this. So we need to remember this, and then we need to remember G and so we need to remember G and 0, well, G and C. So G equals 1 and C equals 0. So G and not C. So I'm just having trouble following everything. So let's have that. X equals is it G and not C? There was an or, I believe. Or C and not L. So it's or C and not L. Yeah, I probably should have planned that before having to waste my time doing that. So let me just check that. G and not C. G and not C. Or C and not L. And that should work. Alright. So we can go ahead and we can get rid of these because we're going to be replacing them with the actual letters. So we need G, C, and L. Just move those. And X stays the same. So we just have to get rid of these gates here. Get rid of that, that, and that. And we can start fresh. So let's go ahead and do this. Let's again work the brackets first. G and not C. So let's have the not in front of C. And make sure it's a little bit far because there is a C here. So just move that there. And we can have the AND gate here. Just move that there and move that there. And then C and not L. So we need another NOT gate. An AND gate. And an OR gate because there's one right here. So we just do that, 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 and that. I'm just going to move this down. Okay. So there's our circuit for this problem. So again, we can test it out. G and not C. So G and not C, that works. C and not L, that works. And a few others which may or may not work. So again, we're going to do the, we'll create the truth table for this. So let's go back to numbers. So that's G and not C, or C and not L. So we can clear just this up, and we can do the same thing we did with the last one. So G and not C, and we better actually change these as well. That would be a good idea. So G and not C, that's one there, one there. Or C and not L, find C not L, C not L, and the rest should be zeros. So let's go ahead and test this out again. I'm going to see if I can memorize this. 0, 0, 1, 0, 1, 1, 1, 0. So 0, 0, 1, 0, 1, 1, 1, 0. I'm horrible at memorizing. What was it again? No, I'm not kidding. I'm actually serious. Okay, let's start. Let's do half and half. 0, 0, 1, 0. So 0, 0, 1, 0. That works. 1, 1, 1, 0. So 1, 1, 1, 0. So see, that worked again. So yeah, that just can save you some time in the exam. And in the next video, we're going to be looking at the NAND gate and why it's so special. That's it. IGCSE Computer Science Syllabus Statement 1.3.1e. Use logic building blocks to build other logic gates and circuits. So this isn't part of, well, I mean, this statement isn't actually in the syllabus, but you still need to know about logic building blocks. And what we mean by that is using like multiple of a number of one logic gate to build other logic gates and circuits. So let's take a look at an example. So let's say we wanted to build the AND gate out of NOR gates. That's a good example. So what we do is put a NOR gate here, a NOR gate here, and a NOR gate here. Connect them. I should probably move that up a bit. Connect that there. Let me extend that, and then we have the AND gate, as you can see. And to prove that this is the AND gate, in case, I don't know, you don't know if this is the AND gate, let's take an actual AND gate, and I'll prove it. So 1, 0 makes 0, 1, 0 makes 0, 0, 1 makes 0, 0, 1 makes 0, 1, 1 makes 1, 1, 1 makes 1. So we've just built the AND gate out of NOR gates. So that's just an idea of how you could do that. So we did that out of NOR gates, but the most popular logic building block is actually the NAND gate. And as I've said in the past few videos, we were going to learn about the NAND gate and why it was so important. Well, this is it. This is the time where we know about it. Now, the NAND gate is really important and popular because, one, it's the cheapest gate you could buy, apparently, and two, you can build any other logic gate with just NAND gates. So let's take a look at that. We're going to build in this video every other logic gate with the NAND gate. So let's start with the easiest one, building a NAND gate out of NAND gates. So all we need is one NAND gate. Extend that there. And as you can see, a NAND gate is built out of NAND gates. To prove that a NAND gate is built out of NAND gates, we'll use a NAND gate here to show you that we can build a NAND gate out of NAND gates. So let's take a look at this. So, well, actually, yeah, 0 and 0 make 0. Oh, 0 and 0 make 1, and 0 and 0 make 1. That's the same. 1 and 0 make 1, 1, 0 and 1 make 1, 1 and 1 make 0. So that's proof that a NAND gate can be built with NAND gates. So let's try something a little bit different. So let's try creating a NOT gate, because a NOT gate is quite an important gate, as you can use the NOT gate to NOT any other gate. So let's try the NOT gate out of NAND gates. So what you need to know with this is basically the NAND gate can be treated as a NOT gate. And by that, I mean we can do something like, oh, no, hang on, that doesn't look quite right. Alright. So as you can see, it NOTs the input. And to prove that, because I like proving things, let's put that there. You can extend that. So when this is 1, this is 0, this is 0, this is 1, and there. That's it. So I'm just going to get rid of all of this and all of this. So we can try building other gates with the NAND gate. So let's try building an AND gate with NAND gates. So we know that a NAND gate is basically an AND gate with a NOT put in front of it. So what we need to do to build an AND gate out of NAND gates is to put a NOT in front of it. So we just saw that a NAND gate can be used as a NOT gate. So all we have to do is this, and there's our AND gate with NAND gates. And to prove it, let's put an AND gate there again. As you can see, 0, 0 makes 0, 1, 0 makes 0, 0, 1 makes 0, but 1, 1 makes 1. So let's get rid of all of this, and then this. So let's try an OR gate out of NAND gates. So this is a little bit different in the way everything is placed. Sort of similar to our AND gate out of NOR gates. So we're making OR gates out of NAND gates, and it's basically the same positions, but we're using NAND gates instead of NOR gates. So let's put a NAND gate there. We can extend that, and there is our OR gate, as you can see. And again, to prove the same here. So that's our OR gate out of NAND gates. Now let's create a NOR gate out of NAND gates simply by adding a NAND gate here. So this acts like a NOT gate. And to prove that, we can replace this with a NOR gate. So as you can see, it's the same as this is the same as this. Let's try something a little bit harder. Let's try the XOR gate. So we remember that the XOR gate looks like that. We put this here. The XOR gate is exclusive OR, so it'll only take one as only one as an input. Anything else, it will be 0. So this is how we do it. It's a little bit trickier. So I'm actually not sure if the course expects you to know this for the XOR gate, but we're going to do it anyway, just to be sure. So what we need to do is add another NAND gate here, add another NAND gate here, another NAND gate here, and a final NAND gate here. And what we're going to do is move this in a bit to give us some space. So there we are. So it's a little bit different how we connect them. So we put that there, and then we put this here, and then put these here like that. And once we've done that, we just put this here and put this. Ooh, it's a bit weird. What I'm gonna do is move this up like here, so it looks a bit better. And then we extend that to the output, and we can test both of these. As you can see, that works. So our final gate, of course, is the XNOR gate. So basically the XOR with a NOT in front of it. So just to remind ourselves what that looks like. The output will be 0 if only one input is 1. So it's basically a NOT of XOR. In fact, yeah, it is the NOT of XOR. So what we do, same principle again. We add another NAND gate here. And acts like a NOT gate. And then reset it. It's 1, 0, 0, 1. And that's pretty much it for the logic topic. And the next topic is computer architecture, which is, again, more about hardware. We actually move on to software quite a bit later, after, I think after storage, I believe, and then we move on to like operating systems or something like that, and then languages and some other stuff. So yeah, stay tuned, and yeah.